Hi everyone and welcome back. In a recent video, I gave an overview of the queue abstract data type by talking about its definition, what type of values can go in the queue, what are common operations on a queue, what's a common variation of a queue, and also how a queue could be implemented possibly using an array, vector, or linked list. So in this video, I want to actually do the implementation of a queue as a singly linked list. So what we're going to do is we're going to talk about how a singly linked list could first be used to represent a queue. What's the front, what's the rear, how do we do our enqueue, how do we do our dequeue, and then we'll head over to our virtual machine and we will code up the solution by using a linked list. All right, so let's begin with an example. Let's say I have this linked list, which I want to represent a queue. So I'm just making up some numbers here. Let's say that there are 3 nodes in my linked list. All right, so I need one end of this linked list to be the front and one end to be the rear of my queue. So naturally you would think that the head of the linked list should be the front of the queue. And that can be the case. We get to decide because we're the ones who are implementing the queue. So let's say we do that. I'm going to put a label and say that the head of this linked list is my queue front. So that means the tail of my list over here towards the end is my queue back or my queue rear. So since we enqueue at the rear, I'm going to write enqueue on this end. And since we dequeue at the front, I'm going to write dequeue on this end. All right, so let's go through our enqueue and our dequeue and see how it's going to work with our linked list. Let's start with dequeue because it's actually just a little bit simpler. So let's say I want to dequeue from my queue, which means I want to remove this node 3 from my linked list. Okay, so since I always dequeue at the front of the queue, I'm essentially always going to be working with the head of my list, which means what I effectively have is a delete at front. This is a common linked list operation. In fact, we've already implemented code to delete at front in a linked list in a previous video. So what would the time complexity of my delete at front be? Meaning, what would the time complexity of my dequeue be? Well, because I do the same amount of work, regardless of how long the list is, I always check if head isn't null. If it isn't, then I grab the reference to the first node, I update head to point to its next, which is 5, and then I use that saved reference to deallocate what was the first node. So I'm always working with the head of the list. This is a constant time complexity algorithm, and its big O is big O of 1. So that's great. So far, our queue implementation is going to be pretty efficient. What about enqueue? Okay, so enqueue is when we add or insert a new node in the list. So let's say I have this new node over here. Let's say it has the value 12. And I want to enqueue this node into my queue. So that means that I have to update this 6th node right here so that it doesn't point to null anymore, it points to 12. So in order to get a reference to 6, I've got to traverse the entire list starting at head. So I would have, head pointing to 5. So I'd start cur node at 5. Okay, 5's next pointer isn't null, so I'm going to advance to my next node, 6. 6 next pointer is null, so that means it must be the last node in the list. So I'm simply going to have this node point as its next pointer to my new node. Effectively, what we just did was an insert at end, which is also known as an append node. So I'm going to write insert at end, aka append node, and the time complexity for this algorithm is actually not big O of 1, it's big O of n. It's linear time complexity because I have to traverse the entire list from beginning to end in order to get that last node. Is there any way we could improve upon this time complexity? And the answer is yes, we can. In a few videos ago, I talked about some common variations of linked lists, and one of them is a linked list that includes a tail pointer. So a tail pointer is a pointer like head at the linked list class level, and it stores null if the list is empty. If the list is not empty, it stores the memory address of the last node in the list. So as long as I keep my tail pointer up to date, then I can always, with constant time complexity, access the last node in the list. I can do so directly with tail. So let's go through our insert at end, aka append node again, and let's see what the time complexity is when we have a tail pointer. All right, now we don't have to traverse the entire list in order to get a reference to the 6th node. Instead, I can just access tail directly. So let's say that I got my new node here again, 12, it points to null. And I can actually write new node here. So new node is this node right here. Its next pointer is null. So tail's pointing to 6, so I can just say, okay, well, 6 next pointer should be new node. So tail's next pointer is no longer going to be null, it's going to be new node. Now I have a new last node in my list, so I have to update my tail pointer so that it no longer points at 6, and instead it points at new node. So now I effectively have a big O of 1, a constant time complexity append node, aka insert node, using my tail pointer. So now my enqueue is just as efficient as my dequeue, and I can access either end of this list really fast. All right, let's start coding this up. So we're first going to have to make some adjustments to our linked list class in order to support that tail pointer and to support delete at front and append node, keeping that tail pointer up to date. All right, here is our linked list code here. This is the same class that I wrote in a few previous videos, so take a look at those if you haven't already. We've got a node here that stores an integer as its data value, and it's singly linked because it stores a single pointer to the next node in the list. Here's our head pointer, and right after this head pointer, I'm going to add another pointer for our tail pointer. All right, here are our common linked list operations. Now, we don't need all of these for our queue. In fact, we only need the ones for dequeuing, delete at front, and enqueuing, insert at end, which is also known as append node. In fact, that's what I named it in our code. So I can delete everything else. But I'm actually gonna at least keep the display list because it's always nice to have for debugging purposes, but I can get rid of the rest of these. Insert and order I can get rid of as well because we're implementing something called a conventional queue where we really do only insert at one end and we really do only remove from one end. But we could implement a priority queue, in which case we could insert anywhere in the queue based on a priority. Think about it like keeping the queue in sorted order where the highest priority or the highest values are towards the front, so they're dequeued first before lower priority or lower values, which are more towards the rear of the queue. We're not going to implement a priority queue in this video, so I'm going to get rid of insert and order. All right, the last change I'm going to make here before we head over to linklist.cpp and start coding up these solutions is to update delete at front so that it returns the value in the node it just deleted, or -1 if the list was empty and there wasn't a node to delete. The reason why I'm doing this is because many queue operations, when they do this dequeue, they want to know what was just dequeued from the priority queue or from the conventional queue. All right, so let's head over to linklist.cpp and let's update our code. So starting at the beginning, for our constructor, we need to also initialize our tail pointer to null. In our destructor, we can leave our while loop as is that walks through each node in the linked list and deletes that node. At the end, for good practice, we should set our tail pointer to null like our head pointer, just so that we can't accidentally access the address in tail that is no longer valid. All right, so we don't need an insert in front anymore. Our display list, we could leave it as is, but for debugging purposes, it would be nice to include some information about where our tail pointer is pointing. So I'm going to add to the end of this display list that if tail is not equal to null, meaning it points to something and it's safe to dereference the pointer, then I'm just going to simply print out what tail points to. All right, in my else block, I know that tail is null, so I'll just print out that it is. All right, our display list is now more informative and will show us information about what tail is up to. All right, next is append node. So we do need to make some updates to append node, but luckily these updates actually make append node simpler, because recall that without that tail pointer, our append node was a big O of n, a linear time complexity algorithm, because of this loop right here. But with our tail pointer, we're going to be able to delete all of that loop code, and it feels good to do so. All right, so let's go through our first case. Our first case is if the list is empty, there's nothing in it. Well, that means the new node we're about to insert is going to be the only node in the list, so both head and tail should point to that new node. If the list isn't empty, then what we effectively have to do is create these links right here. So we're going to have tails next point to new node, and we're going to have tail point to new node. Those are the two updates that we need to make. And that's it. That's our big O of 1, our constant time complexity algorithm for append node. All right, we don't need an insert in order because we're not doing a priority queue, we're doing a conventional queue. We do need delete at front. That's how we dequeue in our queue. So here we do need to make an update. Recall that we're going to return the integer value in the node that we delete. So I'm going to return -1 on failure, meaning the list is empty and we weren't able to delete a node. But if we are able to delete a node, then I'm going to save that value right before we delete it. So I can use node to delete, or I can use value here to grab the value in that node right before we delete it. All right, we do have to make sure that our tail pointer is always up to date. So we do have a little bit more code to write a delete at front. So we're always working at the head of the list. So you may wonder, well, why do we need to update tail? Well, there's one case where we need to update tail, which is if there is one node in the list and we delete that node, then head is going to be null because of this line of code right here, right? So if there's one node in the list, head points to it, which means head's next is null. So we're effectively going to have head be null and our list is empty if there's only one node in our list and we delete it. All right, so what I'm going to do is I'm going to test to see if head is null. If head is null, then I know the list is empty, and that means that our tail has some invalid memory address in it, and we need to override it with null so that both head and tail are null. All right, so that's all we have to do with our delete at front is just make sure that if our list becomes empty, tail doesn't point to an invalid node. We do not need delete at end because we do not dequeue at the rear, we only enqueue at the rear. We don't need delete node because we can't remove an arbitrary node in our queue. And therefore, we are done with our linked list class for now. In main, I just have some simple code here that is appending nodes 1253 and then displaying the list. So since we're always appending a node, we're adding it to the tail of the list. So when we print this out, we should see 12 at the head and 3 at the tail. So let's compile this. And we see 12, 5, 3, head's pointing to 12, and tail is pointing to 3. So initially, our linked list implementation with that tail pointer is looking good. Now, our next step is to subclass linked list in order to implement our queue. So I'm going to open up queue.cpp and queue.h. So these are going to be empty files. Give me a little bit of time here to define some boilerplate code for queue, and then we'll head over to queue.cpp and implement some of these operations. Because we're going to inherit from linked list, I need to include linkedlist.h. All right, so here's where I'm establishing the relationship that queue inherits from linked list. I've got to ask myself at this point if there's any queue-specific state that I need to store. If so, I would need to add attributes to the queue class that are specific to queue, but not general enough for linked list to have. And we don't actually have any specific attributes that we need to provide here. So queue is not going to have any specific queue attributes. That means we can move on now to our common queue operations. So these are going to be public member functions. Okay, so for our common queue operations, I'll show real quickly what we were talking about in our diagramming earlier. Okay, so we've got enqueue, we've got dequeue, we've got peek, we've got isEmpty, we've got size, and we've got clear. All right, so let's start with our enqueue. So enqueue is going to accept an integer argument, which is the value to create a new node for, and then insert into the rear of our queue. For our dequeue, no arguments, but going to return the value in the node at the front of the queue that was just dequeued. And then for our peek, we'll just look at the front of the queue. We won't remove the node in the front of the queue, but we will return its value. And then for clear, this is going to be a void function. isEmpty is going to return true if the list is empty or the queue is empty, false otherwise. And then lastly, we'll implement a size, which is going to be how many nodes, how many items are there in our queue. All right, these are our 6 common queue operations that we're going to implement together. So I'm going to head over to queue.cpp in order to provide an implementation for these. All right, let's start with our enqueue. So our enqueue, recall, it needs to accept an argument. We need to make a node for that argument and then insert that node into the back of our queue. So we need to insert, if I can get this to come back here. We need to insert at the end, aka append, this node in our linked list. So the implementation for this function is actually pretty short because all of our heavy lifting is done inside of our linked list class. So all I need to do is simply call our append node, passing in our argument. And that's all we need for our enqueue. Likewise, our dequeue is going to be pretty short, so we're simply going to return whatever our delete at front returns. Okay, recall that we dequeue at the front of our queue, so we call delete at front on our linked list, which we updated to return a value, and then we simply propagate and return that value back to the calling code. All right, so now for these other operations, these are kind of supporting operations on a queue, not as fundamental as enqueue and dequeue. These operations, as is, are going to need to access some private members of our linked list class. Specifically, we're going to need to access, like for peak, head. So the way that our linked list class is implemented, head and tail are private attributes. What we can do instead is make these attributes protected so that we can access them from a subclass like queue if we want to. So I'm going to make this update to make my head and tail protected so that I can access them in the queue class. So now for peak, I'm just going to test to see if head is not equal to null. And if it's not, I'm simply going to return whatever's at the head of the list. So that's why the return type on peak is int, just like the return type on dequeue is int. If something goes wrong, meaning the list is empty, there's nothing to peek at, I'm going to return -1. All right, let's do our isEmpty next, because it's a short one. So for isEmpty, once again, I'm going to test to see if head is not equal to null. If it's not equal to null, then I know that there's, in fact, a node or an item in the queue and in the linked list. So I'll return false. If it is null, then I'll return true. I know that there isn't anything in the list, which means that the queue is empty. All right, so the reason I wanted to write isEmpty next is, it looks a lot like peak, but also because clear can use it. So we've got some implementation choices for these functions. So for example, clear. So there are two ways to implement clear. So the first would be, we can write a loop right here. In fact, I'm happy to do it now. All we're going to do is have a while loop, while not isEmpty. We'll simply dequeue each node or each item in the queue. So while there's still items in the queue, dequeue them until there are no more items in the queue. IsEmpty will return true, not true is false, and we'll break out of this loop. So that's one way to solve this, using our dequeue operation and our isEmpty operation. And then the second way to solve this would be, we can leverage the destructor code that we already wrote in our linked list superclass. So for example, I might call a destroy list, which is defined in my superclass linked list. That way I could use it in linked list and I could use it in my subclass queue or any other subclass of linked list like stack, for example. So I'm going to add this destroy list here. And then my destructor pretty much already does my destroy list. So I'm going to pull this out and make it into a function. Now I can reuse this destructor style code either from within linked list like I've done in the destructor, or from a subclass like here in my clear. All right, and then the last one to implement is size. So once again, there's two ways to implement size. So the first one would be to traverse the list and count the number of nodes. So the time complexity of this algorithm would be linear, right? Because we have to walk through every node in the list. Is there a better way to do it? Yes, there is. So we could add a count, aka a size attribute, to our linked list class. And then we could just keep that up to date. So like every time, say we append a node, right, which would be like a enqueue operation, we would add 1 to our counter for our size. Every time we dequeue or we delete at front, we would subtract 1 from our count or our size. So There's a little bit of overhead. You know, we need to keep this up to date, but it's worth it if we're going to be querying the size of our queue quite a bit, because this is going to be a big O of 1, a constant time complexity algorithm. So I'm not going to do option number 2 here. It's fairly straightforward. Instead, I'll do option number 1. All right, so I'm just going to walk through my linked list, and I'm going to count every time I encounter a node. So this is kind of a common traversal algorithm for a linked list. All right, so as long as cur node is not equal to null, we'll enter the body of this loop and add 1 to our count. Here's our progress towards our Boolean condition being false, and then we're going to return our count. All right, so now when I compile my code, I'm going to need to also compile with queue.cpp. Oop, I wrote cur head. All right, so I'm getting a little error here saying that node is private. That is true. Easy fix here. I'm going to simply move my protected up here so that I can access that node type. All right, fantastic. So, I mean, if I run this, I'm not going to see anything interesting because I'm not making a queue object, but now I'm ready to make a queue object. All right, so I'm going to include queue.h so I can make queue objects in main. I think I'll comment this code out over here so we can write some queue specific code. All right, so let's do queue. So let's do queue.enqueue, and let's enqueue, say, what was our original list over here? All right, so we were enqueuing 3, 5, and 6. And then let's do queue.displayList so we can take a look at our queue. All right, so 3, 5, 6, and tail points at 6, head points at 3. So we effectively have our original list that we started it with in black. All right, so now let's dequeue, and that should remove our 3 node. I'm going to print out the value, and then I'm going to print out the list again. All right, so we dequeued 3. Now our queue has 5 and 6. Head points at 5, our first node, and tail points at 6, our last node. So now this is after we've done this green operation here. So head points at 5 and then 6. Okay, next we're going to do get our little purple node showing up over here. Next, we're going to enqueue 12, and it should go to the end of our list. So tail should point at 12, and head should still point at 5, and 6 will be in the middle of the list. All right, head points at 5, 6 is in the middle, and tail points at 12. So it looks like our basic operations, enqueue and dequeue, are working. All right, let's explore the remainder of our operations that we implemented for our queue. So let's see out queue.peak. So this should show us the node value at the beginning of our queue, which should be 5. And then let's see out if the queue is empty or not, which it shouldn't be because we have these 3 nodes in our queue. So this should return 0 for false. Then let's clear out the queue and print out is empty again This time it should return 1 for true because the queue is empty, meaning we just called our destroy list in linked list, which deleted all of the nodes in our queue and set our head and tail pointer to null. All right, lastly, let's print out our list again and make sure that those head and tail pointers are null. All right, so right here is our new output where we're peeking, right? So here's the front of our linked list, the front of our queue. It does store 5, that's where we're seeing 5 there. IsEmpty is 0, which is correct. It's returning false because our queue isn't empty. Then we clear out the queue, and then isEmpty returns 1, which is correct. IsEmpty is true, there's no nodes in the list, and both our head and our tail pointer are pointing to null. All right, well, we coded a lot in this video. We have a basic implementation of a conventional queue where we enqueue at the rear, which is the tail of our linked list, and we dequeue at the front of our queue, which is the head of our linked list. Thanks for watching.